Hi, and welcome back. This is the second video for Chapter 3 in your book. In the first video, we spent some time talking about the first law of thermodynamics, and we talked about the different ways that gases can experience a change in state. Now, remember, the terminology that we're using here when we talk about a change in state refers to going from one set of pressure, volume, temperature, and number of mole to another set of pressure, volume, temperature, and number of mole. Okay. So that said, what I'd like to start today's video doing is I'd like to work a few examples dealing with these specific cases. And in this one right here, this is isobaric expansion. So we have a gas that's heated and it's allowed to expand isobarically. Now remember, isovolumetric, isobaric, isothermal, adiabatic. Isobaric means constant pressure. If the internal energy changes by 500 joules and the heat added is 1500 joules, what is the change in the volume of the gas? Now we're going to assume that the gas is maintained at 1 atmosphere of pressure. So what we've been given here is a pressure of 1 atmosphere. Now we know, thankfully, 1 atmosphere is 1.01 times 10 to the 5th pascals. We're also given a change in internal energy, du, of 500 joules. We're given that we have added heat, which means it's positive, of 1500 joules. Now, constant pressure, okay, and we're trying to find the change in volume dV. Now, before we get started with equations, one thing I would like to do is to show you one way that you can treat changes of state in a gas. And that's through something called a PV diagram. Isobaric, isothermal, these types of expansions have very clear paths on what we call PV diagrams. And basically what you do is you plot the pressure on the y-axis, the volume on the x-axis, and you look at how things change from one state to another state. So I'll call this point right here state number 1. We know with a constant pressure that as it goes from state 1 to whatever state 2 is over here, it's a new volume. So as you can see, these things correspond to volumes. They also correspond to, in this case, a specific pressure. Now I'm going from this state to this state during this transition in this direction. From this one volume here to this volume right here to give us a change in volume. All right. So this would be 1 atmosphere right here, 1.01 times 10 to the 5th pascals. Well, you don't know what our initial and our final volumes are, but we can find the change in volume by using the first law of thermodynamics. So if you remember the first law says that when you add heat to a system, you cause the internal energy to change, and you can also do work. Now, for an isobaric gas, we have constant pressure and a volume that can change. This does not change. This does. So really all we're trying to find here is dV. And if I solve for it, dV in this case is dQ minus du divided by P. dQ is 1500 joules. du is 500 joules. And dP, or not P, dP rather, but P is 1.01 times 10 to the 5th pascals. Now, if you do this, it's 1,000 divided by 1.01 times 10 to the 5th. You get, excuse me, about 9.9 times 10 to the minus third cubic meters. So it's a very small change in volume, but it's a positive change in volume. And it's a positive change in volume because when you look at the difference between the amount of energy that you put into the system and the amount of energy that went into the internal energy aspect of your gas, the remainder between this difference is positive, which means that you did positive work. Now, so in this case, we have something that's being cooled. We have 1 mole of gas that's cooled isobarically, and it experiences a decrease in volume of 2 cubic meters. If the gas is maintained at a pressure of 1/3 of an atmosphere and experiences a change in temperature of 25 degrees Celsius, what I'd like to know is what the heat that's been added or removed is. Okay. Now again, let's write down our givens. What are we given? The number of moles is 1.00. We have a change in volume, dV. That's a decrease, so it's negative, of 2.0 cubic meters. Now, the gas itself is maintained at a pressure of 1/3 of an atmosphere. Now, that's 1/3 of 1.01 times 10 to the 5th pascals. So if you do that, you get about 3.37 times 10 to the 4th pascals. Now, there's also a change in temperature here. The change in temperature that our gas experiences, which I'll call dT, is 25 degrees Celsius. It's positive. Now, what are we trying to find? Well, we're trying to find how much heat has been added or removed. So we're trying to find dQ. Now again, I'm going to draw this on a PV diagram. Now, you may or may not need the PV diagram to understand what's going on. But again, we know visually a lot of times it's easy to see things that analytically it may not be easy to see. So again, we have a constant pressure. I'll call it right here. Our pressure is 1/3 of an atmosphere, or 3.37 times 10 to the 4th pascals. Okay. Now our gas is decreasing in volume. So my state is going to start, we'll say, somewhere around here and end somewhere around here, going from here to here in this direction right here. From our beginning state to our ending state. Now this is going to correspond to whatever our initial volume is This is going to correspond to whatever our final volume is in this transition. Now, we don't know what these are, but we do know that it's negative, and we know how much it is. We know what the actual change is. Now, so this is what a PV diagram would look like for this. So here, again, we want to use the first law of thermodynamics. Thankfully, we're dealing with an isobaric gas, which means dW here is a constant pressure times a change in volume. We know the pressure and we know the change in volume, so thankfully we know what that is. du is a little more complicated. du is 3/2 in R dt. This is the internal energy. Now, thankfully, we know what dt is, and we know how many moles that we have. All we're trying to do is to find dq. So here's our first law. It looks like this. This is 1.00 moles. R is 3.184, 814. This is always very frustrating for me. I can never remember R. It is 8.314. 8.314 joules per mole Kelvin. Now, next we have our change in temperature. It's 20 degrees Celsius, or 25 degrees Celsius rather, or 25 Kelvin. The changes are the same in the Kelvin and the Celsius scale. Now the pressure. 3.37 times 10 to the 4th pascals. And the change in volume. The change in volume is negative. So before I actually do the calculation here, what I would like to do is to point out the following. You can kind of see what's happening here. Whatever heat has been added or has been taken away has had the following consequence. We've caused the gas itself to heat up in temperature. But the environment itself, since this dW is negative, the environment itself is doing work on the gas to do so. Okay. So if you plug this into your calculator, excuse me. I have 3/2 times 1 times 8.314 times 25. And then I'm subtracting away let me get this right here in my calculator. The 3.37 times 10 to the 4th. And then I'm multiplying that by 2. And what I get here is a negative 6.7 times 10 to the minus 4th. Or not 10 to the minus 4th, 10 to the 4th rather. Sorry about that. Joules. So what's happened here is the environment itself has done work on the gas to compress it. But as a consequence of the compression, it's caused heating. So the gas is losing this much energy to the environment. Now, here's another one right here. This is an isothermal expansion. What that means is that our pressure can change, our volume can change, all these things can change with the exception of your temperature. Okay? So what I've been given here is that I have 2 moles of gas, and they're being held at a constant temperature. Now, what is that temperature? It's 200 degrees Celsius, which we're going to need to convert to Kelvin. Remember, to go from Celsius to Kelvin, you add 273. So this would be 473 Kelvin. Okay. Now, we're also adding heat. Now, our initial volume, which I'm going to call V1, is 0.389 cubic meters. We're looking for the final volume of the gas. All right. Now, again, you can do a PV diagram. So on this axis is P. On this axis over here is V. We're starting off, I'll say about here somewhere. My initial volume, V1, is 0.389. Whoops. Cubic meters. Now, so this is 1. This is where we're at. Now, somewhere over here, I'll say maybe here, we have a new volume. This is what we're trying to find. Now, the path to get from here to here is generally not a straight line. Adiabatic expansion, not adiabatic rather, but isothermal expansion has usually this sort of loop to it. And that's because there's an inverse relationship between pressure and volume. Now, speaking of which, we also know our pressure. At the beginning, it's 2.0 atmosphere. That ends up being 2.02 times 10 to the 5th pascals. Now, so the next thing you want to do is to write down your first law. So dq is equal to du plus dw. Now, here's the deal though. So if you remember, and let me get my little reference paper over here. There's a lot of stuff going on. Where is my reference paper? Where are you hiding it? Oh well. I'll just do it again. So here, if you look, we're dealing with an isothermal situation. And we know that our gas is a gas during this change of state. So if you think about what the internal energy looks like for a gas, 3 halves nR dt. What you'll see here is that if the change in temperature is 0, that is, it's being held constant, it's isothermal, the change in internal energy is 0 as well, which means that this does not count. And basically what happens is any work you're doing, any heating rather that you're doing to the gas is going explicitly into making the gas do work. Okay. Now, what kind of work are we looking at here? Well, that's the isothermal work. And if you look that up, and we got it last time, give me a second here. Let me grab my my reference. There's a whole lot of noise going on here. My work area. Excuse me. Let's see here. So for isothermal expansion, when you look at the work, you end up with I want to say it's going to be a pain is what it's going to be. Heck, I can't find it here, so why don't I just rederive it, right? This is one of the benefits of how all this stuff sort of ties together. So the heat that I'm going to be adding here is going to be going into work like this. Oh, BV. From my initial volume to my final volume. But we're dealing with an ideal gas. So the relationship between P, T, and the rest of it is through the ideal gas law. Like that. N, R, and T are constant. This is isothermal, so that's constant. If I plug this in for P, you're integrating dV over V from V1 to V2. And so there you go. There's your relationship right there. nRT, the natural log of V2 over V1. So really what we're trying to do is we're trying to find V2 here. We know the number of moles, we know the ideal gas constant, we know the temperature that we're operating at, and we have how much heat that's been added. So if I were to simply solve for the natural log, that's going to be Q over nRT. And then I'm going to take and, raise e to the power of both sides. When I do, the e and the natural log kill each other off, giving me a V2 over V1 on the left-hand side. And on the right-hand side, you have E2, the Q over nRT. So really, our second volume is equal to the verse volume times e to the Q over nRT. And now you can see why it has this exponential look to it. And that's because of the fact that the relationship between the volumes really is just exponential due to the fact that pressure is continuously changing behind the scenes as well. So V1 is 0.389 cubic meters. The amount of heat that we're adding is 3,500 joules. N is 2 moles. R is 8.314 joules per mole Kelvin. And then in the bottom again, you have a T, and your temperature is 473 Kelvin. So you plug this into your calculator. And it's pretty ugly, I know, but it's what it is. 0.389 times e to the power of 3,500 joules divided by 2 times 8.314 times 473. And when I do that, I get a new volume of 0.607. So 0.607 cubic meters. Now, you could, if you wanted, knowing now the number of moles, the temperature, and the volume, determine what the new pressure is. And just for the sake of argument, why don't we do that? So, excuse me, we would use PV is equal to nRT to do that. The pressure is nRT divided by V. R, again, is 8.314. The temperature is isothermal, 473 Kelvin. And the new volume here is 0.607 cubic meters. So our new pressure here is going to be, let's see, 2 times 8.314 times 473 divided by 0.607. And so I see P2 being about 1.31 times 10 to the fourth pascals. So as you can see, our initial pressure was about 2 times 10 to the fifth. Our final pressure is about 1.5 times 10 to the fourth, so it decreases. So here's P1, as you can see, is greater than this one right here, P2. So you have, like I said, this sort of exponential decay to this. Okay? So there are a few examples, like I said. And what I'd like to do now is to talk about what happens when you're looking at the work done by a gas that's not ideal. Now, we're going to stick just with a van der Waals gas at this point. There are other versions of gases that are far more complicated, that require a higher understanding of thermodynamics to deal with. But a van der Waals gas is pretty easy. So, if you were to write down the van der Waals equation here, it was P plus A times N over V squared times V minus N times B is equal to nRT. So there's your van der Waals equation. I keep wanting to put a parenthesis there, but or possessive, but it's not. Okay. So really, if we're looking at the work and what that would look like, what you're wanting to do is to look at this right here. So we need to solve this for P. Okay. So the first thing I'm going to do is to move this to the right-hand side in the denominator. And then I can move this over here to the right-hand side. When I do it, your pressure ends up being nRT over V minus N times B minus A times N over V squared. So to find the work going from, one state to another state, here you're going to integrate P dV, but it's going to be done to this pressure right here as opposed to the ideal gas one. So that's going to be nRT divided by V minus NB minus A N over V squared dV. Now, a lot of this stuff is constant. Like, for example, not knowing an explicit relationship, with temperature here, we're going to assume for the moment that we're dealing with just an isothermal case. So this will be isothermal. Okay. So you can pull the nRT out. So you end up with two integrals. You have one integral that is this, and n, b are both constants. And then you have another integral, which a and n squared, those are constants. And you have to integrate this. Okay, so these are pretty easy to do. With the first integral right here, I'm going to do a substitution. I'm going to call u v minus nb. Du is just dv, which means for this first integral, I end up having to do this integration right here. v1 minus nb to v2 minus nb when I take and I plug those in. And this would be just du over u. So that's easy. That's just a natural log. This one right here is super easy too. We don't have to do any weird substitution here. We have an an squared. I'm just going to write it out. So this is pretty easy. When you integrate this, you're going to get a minus sign out in front, which will flip this to positive. And it's going to reduce this to v as opposed to v squared. So at the end of the day, you end up with n times r times t times the natural log of u. And u goes from v1 minus nb to v2 minus nb. The second integral, like I said, becomes positive now. And you end up with 1 over v, but you have to evaluate that from v1 to v2. So this right here, when you work it out, ends up being a natural log of this minus a natural log of that. And you can use natural log math to turn that into a ratio. So your first one looks like this. Then you have a times n squared, and you have 1 over v2 minus 1 over v1. And this right here would be the work done. And again, I want to be very clear. This would be an isothermal van der Waals gas. You could go through and do this for isobaric if you wanted. But I mean, really at that point, I don't think really a whole lot changes, to be honest with you, because it just depends upon your change in volume. So that said, let me snipe this real quick. I'm going to copy that. I'm going to paste it over here. Because here, what I want to do is I want to look at the work done by acetylene gas held at constant temperature as it expands from 2 meters to 3 meters. And I'm going to treat this as though it is a van der Waals gas. Let's just write down our givens here. We have our initial volume of 2.0 cubic meters. We have our final volume of 3.0 cubic meters. We know the temperature of our gas, which is isothermal, is 30 degrees Celsius, which is the same thing as 303 Kelvin. Now, we're also dealing with a van der Waals gas, and if you look up the characteristics of a van der Waals gas, what you'll see is that for acetylene, the value of the constant A is 4,516. Actually, 451.6. I'm sorry about that. Liters squared kilopascals divided by mole squared. The B constant is 0.0522 liters per mole. Now we're going to have to convert this, to cubic meters and pascals. But let's not forget that there are 1,000 liters in 1 cubic meter. Okay, so let's start with A to begin with. Here, A, to convert it, you note the fact that there are 1,000 pascals for every 1 kilopascal. And you also note the fact that for every 1 cubic meter, there are 1,000 liters. But you got to do that twice because this is squared. Now you have 1,000 here and 1,000 here. One of these are going to cancel each other out. So you'll be dividing this by 1,000. And when you do that, you end up with 0.4516 pascals meters to the 6 divided by moles squared. It's a weird unit. Now for this one, again, we want to note the fact that for every 1 cubic meter, you have 1,000 liters. So I have a factor of 10 to the minus second here, bringing me to that. You have a 10 to the minus third down here, whenever it comes up and does this division. So that's 10 to the minus fifth. So this would be the same thing as 5.22 times 10 to the minus fifth cubic meters per mole. Now, what we're trying to find here simply is just the work. Oh, we also have 1 mole. All right. So it's just working with this equation for the most part. So our work here is nRT, that's 1 mole, times 8.314 joules per mole Kelvin, times 303 Kelvin, times the natural log of, this is pretty big, 3 cubic meters minus 1 mole times B, which is 5.22 times 10 to the minus fifth cubic meters per mole. So as you can see, the mole here and the mole here are going to cancel, giving you cubic meters, and now you're dealing with volumes. You're going to divide that by 2.0 cubic meters, and then you're subtracting the same thing away. Finally, we have the stuff right here. You're adding 0.4516 Pascal meter to the 6 divided by mole squared. A weird one. 2 moles. Not 2 moles, what am I saying? 1 mole, but you got to square it because of that. And then you're just, 1 over 3.0 cubic meters minus 1 over 2.0 cubic meters. All right, so this is what you got to do. So if I plug this into my calculator, let me get my calculator here. And then let's see here. So that, and then multiply by that. And then 0.4516. You end up with 1,021 joules of work done. So, you know, if you keep the sig figs, you got one here. So that's about 1,000 joules. Right? So, a little bit more complicated, like I said, dealing with van der Waals gas, but not too much. Okay, so the last thing I want to talk about in this particular lecture is the relationship between specific heats when you have a gas at constant volume, and specific heats when you have something that's undergoing a change in pressure, or a change in volume rather, in a constant pressure. So to do that, what I'd like to do is to remind you about a result that we got last time. And that was that if you think about a situation, and let's just use the first law again, where you add heat in, you have a change in internal energy, and you have the ability to do work. If you think of a situation in which you hold the volume fixed, so isovolumetric. In an isovolumetric situation, if you look at your work, dV doesn't change, which means that your gas isn't allowed to expand to do work on the environment. And in a situation like that, all of the heating that you're doing goes into changing the internal energy. Okay. And as we saw last time, if you think of the internal energy du as being 3/2 in r dt, okay, and you think of dq as being sort of the chapter 2 version of heating before we really started talking about what's going on, where you are taking your gas and you are heating it. It has a number of moles, it has a specific heat, and you're causing it to change its temperature. When you compare these things, noting the fact that this is held at a constant volume, it's isovolumetric, then your molar specific heat at constant volume looks like 3/2 R. Now, I pointed out then, talking about energy equipartition, that you could write this as d over 2 times R, where the d is the degrees of freedom. Okay. So for an idealized monatomic gas, C sub V is 3/2 R. But what if your gas isn't being held at a constant volume? Well, we know from our discussion way back when, in I think chapter 2 lecture, I mentioned that you have two basic types of containers. They're idealized. You have one that holds the volume fixed, and then one that allows the volume to change by holding the pressure fixed, like a balloon. So let's look at the one that deals with a constant pressure. Well, in a situation like that, when you write out your ideal gas law, or not your ideal gas law, but your first law of thermodynamics, which looks like du plus dw, which looks like, 3/2 r in dt plus p times dv. And you note the fact that 3/2 r is this is just the molar specific heat for a gas at constant volume. So now your dq looks like this. And then you say, okay, so my pressure is constant. Okay. Well, do I know any relationships between, say, pressures, volumes, things like that? Well, sure, there's the ideal gas law. PV is equal to nRT. Now, I want to look at this, and let's think of a situation in which, the temperature can change, but the volume can change as well. If I take the differential of both sides, pressure is constant, so it doesn't change. Number of moles is constant. R is constant. dt is not constant, it can change. This right here can be written as N times R times dt. Okay. Now, so in this case, I'm adding heat in, but I'm holding the pressure fixed. So following this sort of notation right here, I'm going to call my molar specific heat Cp for constant pressure, and it's going to be Cp times N times dt. But on the right-hand side, I have Cv times N times dt, plus N times R times dt. And take a look at this. There's a whole bunch of stuff here that cancels. The dt's, for one, go away. The number of moles go away. And now I have a relationship between the molar specific heat for a gas that has a constant pressure, the molar specific heat for a gas that has a constant volume, and the ideal gas constant. So really what this is this shows you that if you allow a gas to expand, because of the fact that it's expanding, the way it accepts heat is going to be different than one who's not allowed to expand. So the specific heats are not the same. And this is something that you should put in your notes, and you put a big star beside. Now, so that said, there are lots of different types of gases that we can idealize. We're going to be talking about those in much greater detail next lecture. But just to give you a little bit of an insight, the easiest one to deal with is a monatomic gas. And in a monatomic gas, the specific heat, Cp, is just equal to Cv plus R. That's 5 halves R. And Cv is 3 halves R. But the next more complicated description is called a diatomic gas. You're allowing your gas now to rotate and to vibrate. And when you do, our specific heat at constant volume goes from 3 halves to 5 halves, which means that this is now 7 halves. So as you can see, as you increase the complexity of your gas, the way it accepts heat is also changed, which means that you get more correct answers. Now we'll be talking more about this in the next video, and I'll see you then.